Here we're looking at finding the equation of a tangent to a curve. So here are a few tangents, and each of those touch the curve at one place. So we would be finding equations of tangents to a curve. So here's our first question. Now you should note that the key word here is tangent, and from what we have learnt earlier, whenever we have a tangent, or required to find a tangent, we're going to have to differentiate. So here we have y dash, multiply by the power, reduce the power by 1. Now that's the equation for the gradient. It's not the gradient, it's the equation of the gradient, or it's the gradient function. We know that x equals -1, so we can plug that into our x value. So the gradient is 1. Now a tangent is a straight line. We know that a straight line is y equals mx plus c. We're told the gradient is 1. And we've got a value of -1. So we've got y and c. We can't find two things together at the same time, but we know what y equals. Well, we can work out what y equals. We've got equation for y, so we put -1 in for the x, and we'll get a value of y is 2. So put 2 equals -1 plus c, c is 3. Now write out the equation of the tangent. It's y equals 1x plus 3, or y equals x plus 3. Here we want the coordinates of the turning point. So there's the equation. We have to state whether it's a maximum or a minimum point. Now you should know that maximum and minimums we need to differentiate. So that's what we're going to do first. And a turning point, of course, is a maximum or a minimum. There we have a graph. We can see that the top one is the maximum and the bottom one is the minimum. So what we're going to do is differentiate first, multiply by the power, reduce the power by 1. The -24 differentiates to 0. Now we know that the turning points have a gradient of 0. So put 0 equals 3x squared plus 15x. Either solve that on your calculator, use the quadratic formula, or you can factorize and solve, and you get two x values, 0 and -5. These x values are not coordinates, so we have to work out the coordinates of the turning point. They have an x and a y value. So let's put the x in, the 0 in for x, and we can see the y is -24. That gives the first coordinate of the turning point, 0, -24. What about the second? Well, replace the 0 with -5. Work that out on your calculator, and you'll find that it equals 38.5. So here is your second coordinate, -5 and 38.5. You can now answer whether they are maximums or minimums. Now this is really a pathetic sort of a question, because you can see that -24 is lower than 38.5. So the first one's a minimum and the second one's a maximum. However, we can use calculus to prove it. So let's go back to what we have learned in previous lessons, that if you double differentiate and it's positive, you've got a minimum. So let's double differentiate to 3x squared plus 15x, and you get 6x plus 15. Put the first value of 0 in there, and we can see that 15 is positive. 6 times 0 is nothing, plus 15, you've got positive. Therefore it's a minimum, which we knew all along. So the first point is a minimum, 0, -24. The second one must be a maximum, but let's just entertain the marker and pretend that you're really brainy. So we put -5 into there. That's a negative value, so we know that that's a maximum, and that's how you prove it using calculus. For this question, we want the coordinate of a curve, and the tangent is parallel with the x-axis. So there's a pair of axes. The y is not quite straight, but you get the general idea. The gradient of the x is 0. There's your curve, and so we want the tangent to be 0, so that's the turning point. So what we're looking for is a turning point. You know to differentiate to find a turning point. So differentiate it. The gradient is 0, so you put 0 because 64x, so x must be 0. Now the gradient is a straight line, so we know that y equals mx plus c. We've got m and x. What is y? Well, we've got an equation for y, so put 32 times 0 squared plus 1, and y equals 1. So 1 equals 0 times 0 plus c. Write out the equation of your tangent again, y equals 0x plus 1, or y equals 1. And we're done.